what an open set is. Let's look at an open interval. So here is our open interval. Let's say this is 0, this is 1, this is 3. And this set, let's call it A. Okay, so this is a more of a more specific idea of an open set right here. What you have is an open interval, endpoints of 1 and 3, not included in the set. This set A is an open set because it's an open interval on the real number line. A is a set because A is this thing here. It's all the numbers between 1 and 3, not including 1 and 3. So this is called an open interval. It's also considered to be an open set. This idea is kind of a limited idea. Limited or idea of what an open set is. So what we're going to do in this definition by Krantz is look at a more of a general idea of what an open set is. And before we go on, so this, what is this thing? This A is a subset of the real numbers, right? It's a subset. It's a set. It's a subset of the real numbers. All right. So here, let's draw our set U. And oh, okay. All right. So set U. Now let's make it this big. Here's our set U. And set U is called an open set. Doesn't it look like a, it looks just like that one, right? I just switched the colors. Yeah, right? This is an open set, but in the general sense, if I put in a neighborhood like right here, if I take any number in this set, let's say X, and I can create a neighborhood around X using an epsilon of any of the epsilon. There is an epsilon which will allow me to make a neighborhood around this number X, which is still within U. I can choose this X right here. All I have to do is make the epsilon very small. I can go to the left of this X here, and the epsilon, I just have to make it smaller. And it will still be inside this. So in other words, this interval here, if I call this A is within U completely. So in other words, actually, I would write this. This guy here, this set here is a subset of U. If this is always the case, give me pick any element of U, and if I can put a neighborhood around it, which is contained inside this set U, then set U is an open set. Okay, so now I'm going to actually write the definition here. I'll delete this. Well, let's keep the diagram there. So we are open sets and epsilon neighborhoods. This is called a neighborhood that I created. So the definition goes, a set U, which is a subset of R or the same as R, because give me any element in R and I can create a epsilon neighborhood around it, which is fully contained in R. Contains means subset. Okay, or okay, it's called, so this set here is called open if for each X in U we can find an epsilon, right? So we go, there is an epsilon, a positive number, such that the interval is contained in okay. So this is an open set because the endpoints, both the left and the right, are not included in it. This is an open set. It's also called an open interval, but this is not the journal open set. The journal open set is another. In fact, this could be this guy here. These could be its endpoints. So this U could actually be A, comma B.
But the other deal is that it's R, so it could be on either side.
Yeah, if it's equal, R itself is an open set.
Yeah.
So this,
That's interesting. Divergent.
so this just adds this condition there.
Yeah, and that condition is what the open set is. Right?
This itself is an open set.
Yeah.
What a general idea of an open set is that it contains within it every element in an open set. If we drew an interval around it and made it into another, if we started creating for each element an interval, an open set around it,
yeah, you can have an open set for every element.
and it will be within the set.
And it will be within the set.
Yes.
If it was a closed set, then your A and your B.
So let's see, we do this, right? In this case, if we did, this is a half open set, right? And here, let's say this is our X, right?
You can't do X minus
So
X.
now we can't, because if we did that, this, however small the epsilon you make, it's going to contain,
Yeah, you can't.
yeah. So you will have this problem right here.
X minus
And
X
therefore, and this guy is not contained in the set here, right there. So that's it. And and this idea of open sets is what shows up in the proofs, not this simpler idea. This simple idea just says that if the endpoints are not included in the set, set, this says this condition, and this condition shows up everywhere.
Yeah, this says that in that every element needs to be able to own sub-interval of the
Yes.
set U.
Yep.
And that sub-interval has to be,
Hmm.
yeah, it has to be a sub-interval of U.
Now, another way to express all of this, so let's keep this here, and I'm going to write it down here. And this is from my professor over there. Yeah, over there. So here we go. This is another definition of a, this is Francis Sue, the Harvey Mudd professor. Okay. Sue, Chinese dude, but Chinese American. So. And he says a set E is open if every point of E is an interior point. Okay, so what is an interior point? If you draw a neighborhood around an interior point, if you draw a ball around an interior point, that better be a subset of the set E. Every point in E, if you draw and with the radius R, it better be inside it, right? Yes. So here we go. So let's draw this. So this is our 2D. Right. So this is a 2D definition. Yeah. And then pick any point. And why is this an open set? Because it has an open boundary, which means the boundary points are not included in the set. Therefore, we don't, if boundary points were included, then we would end up with this situation, which, and that is not fully contained in set E. So we don't get that. The only points we can consider are the ones that are right next to the boundary point, but between this boundary point, between this interior point and the boundary point, there are infinitely many. So we can always find the radius. If we can call it epsilon, actually some books do that. Actually, Lay does that. I didn't like that, but so the radius, we can find a epsilon radius which is small enough so that this point here has a neighborhood which is fully contained in the set. Yeah, we've actually defined the definition of interior point is that it's a point whose, if we put a neighborhood around it, a ball around it, is contained in the set, which sounds just like this definition. This definition is a definition. What this definition is saying is that this X is a interior point.
Oh yeah, that's saying
So yeah. So in other words, we could have rewritten this. We could have said a set U is a subset of the real number. Okay, set U is an open set if each of its points were an interior point. And then what is an interior point? Interior point is in a point of a set. If you draw a neighborhood around it or a ball around it, that ball is fully contained inside it. So you kind of displace the same definitions around. Yeah. And so you need to, now if we had, so if this was not an open set, if it looked like this, E, then we would have to because every point in E better have a neighborhood that's contained in the E. Then you run into this trouble. Yes, exterior points are coming in. This is not an interior point because all these points are not in the boundary points are not interior points. They're in fact not elements of E. The only elements of E are the points in red. And here, all the elements of E are the points on the boundary are included in set E and also inside. So if you make a neighborhood around this point, that's fine. But for the boundary points which are included in E, yeah, because it's, this neighborhood and its points are not fully contained. Yeah, that's true. This contains an infinity. This set also contains an infinity of points. It's like weird.
That one's a finite and that
Uh,
one's no finite boundary. This one has a finite boundary. That one.
shit. So that's a closed set. It's a closed infinity. This is an open infinity. There must be terms for this. Where you're going?
Because it makes me think about space.
Yeah.
Like,
They're still arguing about that shit. Where does it end? Is it? It's fucked up. Okay. All right. All right. Now I'm going to give you another definition. Huh? Okay, I'm going to give you a definition by Rudin of what an interior point is. So let me write that right here. So interior point, Rudin. Rudin is very shit. I'm not supposed to act funny.
no funny business.
Do not make fun of Pakistani accent. Why not? What the fuck is wrong with you? Oh, we can kill them and bomb them, but we can't make fun of them. So we can't make fun of. We can't. So we can't make fun of South Lebanese people, but we can kill them.
No, I mean, don't you mean that we're remembering them?
Their humanity. Oh, even in a racist.
Yeah. So if we eliminate the jokes and the racist.
And that's the other thing they were saying, that the people who run America have no sense of humor. No. All right, here we go. So the first definition is of an open set, and this is from Rudin. Rudin. This is the hardest textbook ever written for undergraduates. Rudin. It is the best in the sense that you have to learn from other books so you can read what Rudin is doing, because it's very
Super rigorous, right?
Yeah. Okay, so Rudin says let X be a metric space. F. There's a list of definitions A, B, C, D with so that's F. Okay. And for us, metric space is we imagine it as this one, right?
So we're running R squared and
so R is also metric space. R squared is also metric space. R3 is metric. RK is metric space. We just need to imagine this one for this, just for the hell of it.
And so R squared is our space. Our metric is.
Yes. And D is the Euclidean metric. So R space is this, or E for Euclidean, which is, we're talking about x's, x-axis, y-axis, and Pythagoras theorem can be applied. Triangle inequality rule is there.
Okay, so
the distances are positive in this space.
So X is our metric space, right?
Euclidean distance function. So this is distance, and it's going to be this one here. Take 2 points from R2, subtract them and put them in absolute value. That is our formula.
That's what this.
And but these two guys are, remember?
Is that a coordinate system?
Yes. So this is a vector, this is a vector. So when we subtract it, we have to use this formula. So x1 minus y1. So first coordinate of this minus first coordinate of the y vector squared plus second coordinate of x minus.
Scalars
Yeah.
Yeah. Right.
Yeah.
So I hat, j hat, that sort of vectors.
Yes. Same thing as from physics.
Yep. Okay. So
Okay.
then, are Euclidean is just our measurement?
This is Euclidean because this comes straight from Pythagoras theorem.
And I guess my question is it pertains to the coordinate system that we use, right?
It's a Euclidean metric because we are saying we're going to just do this. If there are other metrics too, so there is there's a metric where if x equals y, then the distance between x and y is supposed to be 0. If x vector x is not equal to vector y, then the distance between these two guys is 1. So that's another metric that you can apply, discrete metric. And so and it's very confusing. So I've been trying to understand that. So we'll do that next time when we come back to the metric thing.
Okay, but we're sticking to
Just this simple stuff. Yep. And there's another one where everything, there's a car metric. There are lots of different metrics that you can apply. Euclidean is just this. Take the difference and apply the absolute value sign on it. That's it. Very good. Okay. So now the definition F goes, assume that X is a metric space. And for us, just to understand that, we'll say we're dealing with R2. And the definition goes, I have become the doorman. I don't know who they're looking for. Yes, you looking for somebody or just studying? Oh, okay. Well, it's no. This is a graduate student lounge, so I just let you guys in. You can sit right there. Oh,
we've been going back there. That's where my
oh, go ahead then. If you've been, just pretend I didn't let you in.
thank you so much.
Yeah. If they come for you,
We never mentioned.
yeah, okay, good. STEM students. Yeah. Let's just go back to E. So E, the set E is open. So E is a set here. So it also says, so E is our set. E is open. So this is the definition of open set. In the general sense, right? So I'm going to put in the general sense. The one that will be used all over the place, not our little open interval. E is open if every point of E is an interior point. Interior point of E. That is the key deal here.
And E is a subset of R, right? And X is
Yes.
space. And X equals R.
Which I think he doesn't do that in the definition, but that is understood. Yeah. So the other author does that. Now, oh, this is like proofs, calculus definitions for the, yeah, so it's a real analysis. Yes. You're welcome to join us. Okay. Now let's do this. So it's kind of like a weird thing, right? So now the definition of Rudin definition E is a definition of interior point. A point E, and we could even just actually make that. A point P is an interior point of E if there is a neighborhood. Yes, epsilon neighborhood. Neighborhood is an actual term. Yeah. Neighborhood N, and it actually names it N of P, the point P. So point P is an interior. So point P is a point of set E. It's considered an interior point of E if there is a neighborhood. Yes, exactly. Very good. I have to actually look at it, and it's a proper subset of P. Yeah, because then it's yeah, then we're not really we're talking nonsense. And so what you do is you do this, you go N, and then you put the radius here. We could do epsilon here. Equals, no, not equals, subset of E. Yeah. Yes. So let's do it. We got E. And this is our set E. It's an open set because it's an open set. First of all, it better have an open boundary. And then all the elements of this set, if you drew a neighborhood around it, that neighborhood is a proper subset of set E. Always. And this is the epsilon. Go ahead. What was the question? We can represent that on we can represent E on a number line too. It's the same thing. Okay. So for instance, and here is our set E, and each point P given any we can always create a neighborhood around P that is subset of set E. Yeah. What I saw was that these pictures are more. The 2D pictures are really. You can do that too. Also, another point here. The boundary, we talked about that. The boundary of E has infinite number of points. The boundary here has only 1 point and 1 point. That's the other difference. So this is the boundary is only the one end point. So, but if you draw a whole circle, you're talking about infinite boundary, right? Yeah. So your set E better look like this, right? Your set E is actually, so you can't really see that. Let's say this is our, so I really got hang of all this when I started looking at Francis Hughes diagrams. Not, these lines weren't cutting it for me. Okay, let's do another. We're just not doing it in, we did isolated points already. Let's do the closed. Okay, so this one's a difficult one. No, actually we did the closed set, right? No, no, we didn't. We did open set last time. We did, and we just, I said something about an open or a closed set. Okay, let's do closed set. It's kind of complicated. Okay, so limit point,
Oh, so the closed set, yeah, we did do a little bit of closed
yeah, okay, so we did do that, right? Okay. Let's write down the definition of a limit point, which we didn't do. We never actually wrote it down. So let's write that down. We just wrote down the definition of interior point from Grudin, and now we're going to write down the definition of a limit point. There we go. All right. Okay. This is 2.18b. The problem with this book is there are no pictures, literally almost. Yeah. Like, dude, I'm from Pakistan. Give me a break. Point P is a limit point, can be considered a limit point, is a limit point of the set E if every neighborhood of P contains a point Q which is not equal to P, different from P, such that Q belongs to E. Q is a element of E. Okay, so this definition does not give you any sense.
Yes, it does.
Yeah, but because we've already gone over it. But let's see. So what we did last time was, I think we did do this kind of. So I'm going to draw a set E, and I'm going to have. So this is what our set looks like. This is our set E, and then let's do. So this is our R and R2 and our R1. So let's do R1 here. We have a set E here. Yeah, let's make this red. This is our set E. All right. So it says here. So this number is included. There's just 1 point here. There's just 1 point here. This one is not included. So it's half open, right? We have a half open set. And then it says a point P is a limit point of set E if every neighborhood of P contains a point Q. So in addition to, so let's say we have a set P here, point P. So I put a point P there. And it says, is this an interior point? Yes. But is it a limit point too? It says a point P is a limit point of the set E if every neighborhood of P contains a point. So every neighborhood that I draw around this point P contains other points of set E as well. So I'm going to draw a neighborhood around this. And here are the other points, right? All of these are Qs. If my radius, my epsilon is very large, I'm going to get more Qs. But if, let's say my radius is really small, this is a point P. Is there a Q in this neighborhood? Yes. Q represents all other points than P. There are infinitely many, there is a P and then infinitely many Qs. We just chose to call one P and everything else Q. Okay, so not only is this an interior point, P is an interior point because its neighborhood is fully contained in set E, right? And second, it is a limit point because it contains other elements that are not equal to P in it. Now the thing, and a limit point. It's a limit point that is not interesting to us.
So a closed set is a set that all limit points.
Yes.
And an open set is a set that contains all limit points. All of those limit points.
Better be interior. Yes. So now let's look at another point here. This point here, this is our new P. Let's test this definition. Is a point P is a limit point of set E. It never says P has to be, right? The definition never says this. Yeah, it doesn't have to. It can be this or it can be this. Both P's are fine.
Oh, so this is getting to the definition of upper bounds, like least upper bounds. Because you can throw your point P.
It is literally the, yes, yeah. Because last time what I did is I made a sequence of numbers approaching P, all the terms of the sequence from the set E, but the limit point was not in that. So we could have a sequence of numbers. So we have Q1, Q2, Q3, and they all converge on point P. Point P itself is a limit point. This sequence that we've chosen from this infinite number of real numbers, we chose like maybe 10 of those. Those 10 points seem to be heading towards clustering around P. And it's an increasing sequence, right? Okay, so we have that. Is this a limit point? Yes, because if I drew a circle around it, a neighborhood or a ball, right? Neighborhood, the other term for neighborhood is ball. And it doesn't matter how big or small the radius is, it will contain Q's in it. So this is a point on the upper boundary, which means P is not an element of the set E, but it is a limit point because its neighborhood contains Q's elements, elements of E, the Q's.
So it depends on our size of our epsilon.
Yeah, we'll always have infinite number of Q's because we're dealing with infinite. Every little square inch, it's kind of like the deep space picture of the galaxies, right? And then you look at that little thing, that inch has millions of galaxies in it. Yeah, yeah.
You have an infinity.
What is it called? The deep something, I forget. It's called the deep. There's a term, it's a really cool term. Now, let's say I pick P right here. This P is an element of E. Yeah. Limit point, limit point. Now, this P belongs to E, right? Because it's on the closed boundary. And this P also, whatever the size of the radius, will contain points Q that are elements of E. Q has to be the element of E. So now let's put a isolated point here. This is our P. And this P is an element of E. This P finally is an element of E.
Oh, but it's not.
But it's sitting here, right? We could put P right here.
So it's an exterior point.
Yeah.
Exterior point.
So, and I don't know if there's a term called exterior, but yeah, so there isn't, but yeah, go ahead and use it. Well, so here it is. Let's just call it isolated. That's the term for it. So isolated in the sense that this is a point of set E isolated from its brothers. So
You and Eric.
the I'm isolated. So this so this P is an element of set E, but it's out here isolated. And why is that? Because anyway, so and we're going to go to that definition next, isolated point. But this P, if I draw a very giant neighborhood around it, then it will catch a Q, but not for every epsilon. Every neighborhood. But this guy has no Q in here, no Q here. Therefore, this element of this point P, an element of set E, is not a limit point. Because the thing is, the whole business of limit point is that there are other Qs that are impinging on, moving toward. There's nothing going on here.
No, it's
Yeah. And so what is an interesting limit point? Not this one, but this guy and this guy. Unless we chose this P to be a limit point where there's a sequence approaching it, then this becomes an interesting limit point. Depends on it. Because the limit for our sequence, we could have chosen this number. So then this becomes an interesting limit point.
Well, then would that change
No, the set remains the same. We just chose only a sequence of elements from it and call it with a formula.
So it's a sequence that is.
It's a sequence that was generated by this formula. As you change n, you get the next and the next and the next, and that next ends up going like this, but it ends up going towards this guy here, towards a limit point to its limit if it converges.
Isn't that a divergent formula?
It could be. I mean, I'm just random. All right, now let's do isolated. I think that's Yeah. Okay. Let's look at isolated. Where is that definition? Yeah. And then let's go to Rudin. So how about tomorrow? Do you want to, we could do integration, but, or you should study now.
I've got a textbook.
Okay. All right. Yeah. No, I mean, integration from this kind of weird. Let's just meet again next week. So
Yeah.
Saturday is off
Yeah.
for me too, because I have to
We need
go.
a day off.
I have to go to the mosque. We are worshiping the devil. Oh shit! I forgot to do this.
The same God.
Yeah. Okay. So limit. I forgot to do this. So this was our. This looks like we're still on limit point. We haven't got to isolated. I forgot to. So you can write this here. Here we go. So this was our picture, and I need red here. All right. So so P is an element of set E here, and this is not a limit point because for because its neighborhood for every epsilon is not does not contain elements other elements of Q. There is no Q here. No Q. We got a bunch of Q's here. Q, 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 Q. Yeah. Now I put P on the open side here, which means if this was 3, this will be RP because there's only one, right? We're on the real number line. And this, it doesn't matter how small the radius is, the neighborhood will catch fish, will catch Q right here. Q's here. So this neighborhood will have Q's that are not equal to P, Q's that are elements of set E. Therefore, 3 is a limit point. And then this guy, if we choose to test, if we choose this to be our P on the closed side of this interval, let's say this is 1. If I drew even the tiniest, smallest neighborhood ball around this point P, it will have many Q's.
Okay.
And if I go right in the middle somewhere,
Also,
yeah, yeah.
So a point on the closed boundary satisfies the same conditions that a point that satisfies. A point on the open boundary satisfies the neighborhood.
Yes.
Outside of the set that belongs to the set
Does not capture any.
does not satisfy the neighborhood condition, but is still a part of the set.
Okay. All right. And so this element of the set is not a limit point. So not a limit point, limit point, limit point. In fact, every Q is a limit point too, right? Or it is not equal to the R next to it.